Welcome to Module 8, where in this mini lecture we're going to talk about some of the background with a one-way ANOVA. A summary of the learning objectives for this module is that you should be able to explain the rationale for a one-way ANOVA and how one-way ANOVA and a two-keys test results are calculated. You should be able to interpret hypothesis test output for a one-way ANOVA, the two-key test, and Wilcox and Wilcox tests, and understand the assumptions for the test and determine whether a parametric or non-parametric test is the most appropriate. Now, when we have statistics that we want to calculate for two independent treatments, we can do a two-sample t-test, which you've learned in the prior module, or you can do what's called a one-way analysis of variance, and we use this when we want to compare the means of two or more groups. This is a parametric test, and when we have two or more treatments, this is a common experimental approach. So we might have a placebo and two different drugs we want to try, or we might have non-smokers, people who are smoke less than 5 cigarettes a day, people that smoke a pack a day and 2 packs a day. So having more than two treatments is actually a common experimental approach, and ANOVA is quite commonly used. When we're looking at the statistics in a situation where we have three independent groups, our null hypothesis would be that the population means for these three groups or three treatments are equal, and our alternative hypothesis is that at least two of the means differ when we're doing an ANOVA test. It won't tell us which two of those differ. That's when you go on and do a two-keys test. But again, to reiterate, the null hypothesis is that all the means for the groups or the treatments are identical, and the alternative hypothesis is that at least two of them differ. It could be that all of them actually do, but that would be determined in a post hoc test. In this situation, if we have these three means that we want to compare, you might be wondering, well, why can't we just do multiple t-tests? So if we did this, we would have three different t-tests. And the first one we compare the means of groups 1 and 2. The second one we would do 1 and 3, and then we would do 2 and 3. But there's a problem with this, and there's a reason why this isn't done. And the problem is that our alpha, remember this is our type 1 error rate, which is related to the probability of rejecting the null hypothesis when the null hypothesis is true, and this is 0.05 for each of these comparisons we would do, but we want an alpha of 0.05 for our whole study that we're doing, for our whole experiment. And with an alpha of 0.05, the probability of not making a type 1 error then is 0.95. So if we did these three different t-tests separately, the probability of not making a type 1 error for our entire experiment would be multiplying 0.95 times 0.95 times 0.95 because we'd be doing three different tests. So overall for our whole experiment, the probability of not making a type 1 error would be 0.857, and that's not the same as 0.95. So for a whole experiment, alpha would be 1 minus 0.857, which would equal 0.143, and that would mean that there would be a 14.3% chance of making a type 1 error by doing three t-tests in order to analyze this data. And ANOVA keeps the whole experimental-wise alpha at 0.05, and that's what we want to be doing. So with a one-way analysis of variance, or a one-way ANOVA, it maintains its alpha of 0.05. Again, here's our null and all our alternative hypotheses. And the interesting thing here is that it's an analysis of variance. So here's our symbol for variance, right, sigma squared, but we're actually comparing means. I'll explain this in a little bit more detail in a minute. And the idea here is that instead of using a t-distribution, because we're now looking at variance, we use an F distribution. And F is when you have two variance values that you're dividing one by the other. For the one-way ANOVA, we're interested in comparing the means from two or more of these sampled groups. And here's our null hypothesis and our alternative hypothesis. And our test statistic, remember, is based on variance, and it's equal to the variance of our treatment effect divided by the variance that's due to error. On the right-hand side of the equation here, you can see this is calculated from our sample, so our estimate of our sample variance due to treatment effects due to our sample variance due to error or the random sampling variation. This is what the F distribution looks like. Note that because we're dividing a variance value by another variance value. We're not going to have ever any negative values because these are both squared, so that intuitively should make sense. And we can see that there's a skewed distribution, and we're looking at our alpha being all in that right-hand side tail. When we think about this, if the value of f is equal to 1, then the null hypothesis is true, because there's no added variance due to the treatment effect, right? Because a value greater than 1, we'd have a larger numerator than the denominator, so a larger variance due to treatments than just due to random sampling error. If our value of f is greater than 1, the numerator value is inflated, indicating that there's an added component of variance due to differences among the means. An important thing to consider with the one-way ANOVA are a series of assumptions, including that the data are normally distributed, that there's a homogeneity of variance of data, which means that the variance of the data from the populations is equal, and that the data are independent or random samples from the population. Now I'm going to walk you through an example about how to think about these one-way ANOVAs. So remember that our null hypothesis is that the means, for example here we have 3 groups, and that they're all equal, and that our alternative hypothesis is that at least 2 of the means differ. So for an example, if our null hypothesis is true, what would we expect our data to look like? So imagine that we have normally distributed data. This is one of the assumptions of an ANOVA. And so here's our distribution of our data and our population mean. So that's for our population 1. We'd have the same value. Remember, if our null hypothesis is true, so if our null hypothesis is true, all of these would overlay each other almost perfectly if our null hypothesis is true. Note that with our assumptions, we assume that they have equal variance, and with that we mean essentially that the distribution of the data is the same. I'll get into more detail in that in a second. If our null hypothesis is false, there are some different things that we might see. One is that if our null hypothesis is false, remember our null hypothesis is that our means are all equal, we might see something like this. Where if this is the value of the mean, here's small values and large values, that the mean of group 1 is smaller than the mean of group 2, which is smaller than the mean of group 3. So in this case, we might expect the null hypothesis is false, and each of these groups would be significantly different from one another because there's no overlap at all. Again, remember that they'll have approximately equal variance or equal spread in the data. We might have a scenario where we have some overlap in our data. Right, so here we have our difference between our mean values, and we don't see much variation between our means relative to the variation that we see in our data. Right, so when we're thinking about dividing our treatment variation, or variance due to treatment effects, divided by the variance due to error, the variance due to treatment effects is related to the means, and the error has to do with the variation surrounding each of the means, so within the populations that are being sampled. So here, our null hypothesis would also likely be true because there's more variation within groups due to error than there is between those means. Or another scenario we might see if our null hypothesis is false is something like this, where maybe one of our values is much lower than some of the other values. So in this case, we might expect that the mean for population 1 is significantly different from the means for number 2 and population number 3. Now I want to make a note about unequal variance. So in this case, remember, the assumption is that the variance between the groups is the same. That's called homogeneity of variance. If we have unequal variance, we might see something that looks like this. So if we have unequal variance, and we're therefore violating the assumptions of ANOVA, we might have a case like this. So there's our mean for group 1. Over here is our mean for group 2. And there's our data for the mean of group 3. This violates the assumption of ANOVA. Given data like this, it would be very difficult to have confidence in any results related to significant differences among the population means, right? Because 1 and 2 might look like they're different from each other, but 3 is just swamping all of that variation. So that's why the idea of having equal variance or homogeneity of variance, like we see in all of these other examples up here, is an important consideration with ANOVA. So if you see unequal variance, you don't want to be doing an ANOVA with that data.